this video, we're just going to do a bunch of extra counting practice of all different sections. So I guess sections 1.4 to 1.6. So we're going to start with a card example. So just to remind you, in our standard deck of playing cards, we have 52 cards. That means there's 4 suits. So hearts, diamonds, clubs, and spades. Each of these suits has 13 different ranks. So the ace, or like the 1, so 1 to 10, and then jack, queen, king gives us 13. Hearts and diamonds are red, clubs and spades are black. So there's 26 cards of each color. And there's 13 cards of each suit, 4 cards of each rank. So for each suit, there's 1 card of each rank. And for each rank, there's 1 card of each suit. So let's try and answer some questions relating to the deck of cards. So in your game, you're going to have a 5-card hand. Okay, so when it says 5-card hand, the hand sort of implies that the order doesn't matter. Okay, so when you pick it up, you can rearrange your cards. So the order that you get them doesn't make a difference. So how many different hands are possible? Well, there's 52 cards, and we're going to be dealt 5. So that means we need 5 of 52, where the order doesn't matter. So it's going to be 52, choose 5, or 2,598,960 different hands. How many of these hands have only black cards? So what we do is we restrict to the 26 black cards, and we still want to pick 5 for our hand. And again, the order doesn't matter. Okay, so now instead of 52 cards, we're going to have 26 cards, and we're picking of the black cards, we want to pick 5. So there's 26 black cards, we want to pick 5 of them. This is 65,780. Okay, what if we want our hand to have exactly 3 diamonds and 2 clubs? Okay, so that's going to give us 5 cards total. Okay, so what we're going to do is use the multiplication principle, and we're going to select 3 diamonds, and then, so multiply, we select 2 clubs. So we know that there's 13 of each type, so there's 13 diamonds, and we want to pick 3 of them. And then, because we haven't picked any clubs, there's still 13 clubs, and we want to pick 2 of them. So if you compute this, you're going to get 22,308 different hands of that type. Okay, so let's try another one. This one is a bit harder. So here we want how many hands are full houses. So it's okay if you don't know what that means. Okay, so that's 3 cards of one rank and 2 cards of another rank. So to draw you sort of a picture here. Okay, so we have 3 cards of one number and 2 cards of another number. Okay, so maybe it's aces over here, and then maybe it's 7s over here. Okay, and then our suits, so in order to know what card it is, we need the rank and the suit. So maybe for the aces, we have hearts, diamonds, and spades. Okay, and maybe for the 7s, we have hearts and diamonds, for example. So this is actually similar to the shoe problem. So the idea here is that each rank is in a group of 4. Okay, so there's 4 of each rank, and we want to pick 3 of one rank and 2 of another rank. So what we want to do is break this up. So when you get a card, it's going to take you 2 steps. We want to know both its rank and then its suit. because the ranks are what's important here. So what I'm going to do first is select a rank for the triple. So the one that's going to have 3. So there's 13 ranks, and I want to pick one of them. Okay, so I pick 1, so here we would know it's aces. And now among that rank, we want to select 3 of the 4 suits of that rank. Okay, so there's 4 suits, and we want to select 3 of them. So that's going to be 4, choose 3. Now I need some more cards. Okay, so I'm going to need a rank for the double or the pair, and then I'm going to need suits for that one as well. So we've already used up 1 rank over here, so there's only 12 ranks left. So I'm going to do 12, choose 1. And then once I pick that rank has 4 suits still, and I want 2 of them. So it's going to be 13, choose 1, times 4, choose 3, times 12, choose 1, times 4, choose 2. So if you compute that, you should get 3,744 different hands. Okay, slightly different but similar. What if you have a hand that has exactly 2 pairs? So that's 2 cards of one rank, 2 cards of another rank, and 1 card of a third rank. I find it helps to sort of draw a picture of what you're working with. Okay, so this is what I want it to look like. Okay, so I have a pair, another pair, and then a single card that's a different rank. So I'm going to need 3 different ranks here in total. Okay, so maybe we have, I don't know, let's stick with the aces. Maybe we have a pair of 2s, and then maybe we have a king by itself. Okay, we need suits for them. Okay, maybe hearts and diamonds, hearts and spades maybe, and then, I don't know, a diamond over here. So that would be an example of a hand that had exactly 2 pairs. So remember what the shoes, if you were picking the same number of shoes, you wanted to pick that type at the same time. Okay, same idea here. For these ranks, we have the same number of cards. Okay, so those 2 ranks are actually special, but not from each other. Okay, so this king is actually more special because he is a different number of cards. So when we're doing this, we're going to have 2 ranks for the pairs. Okay, and then we have to pick suits for each. So that's going to be, from our 13 ranks, we want 2 of them for pairs. And then I have 4 suits of the first one, and I want to pick 2. And then I have 4 suits from the second one, and I want to pick 2. And then I need my last card. Okay, so I'm going to do a rank for the single card, and then a suit for it. So I'm going to have, I already used up 2, so I only have 11 ranks left, and I want 1. And then I need a suit for that rank. So I need to choose 1 suit from the 4 that are available. And if you compute this, I'm going to write the number up here. It's 123,552. So these last ones are quite a lot more challenging than the ones above, because you want to make sure you get a certain number of cards from each sort of category. In this case, it was the ranks. So when you're doing that, you have to be a bit more careful. For all the ones above, we just needed to pick some cards from a very particular category. Okay, so all the cards, okay, we're picking only from the black cards. And in part C, we knew exactly which groups we wanted to pick from. So we didn't have to also pick the groups. Okay, so you could make part C a bit harder by not knowing it's diamonds and clubs, but saying 3 of one suit and 2 of another suit. So maybe try and do that one on your own and see if you can reason your way to the answer. It's going to be more similar to D and E then. Okay, let's try something different. Okay, so here we're making a 6-digit PIN number for our debit card, and we want it to be 3 numbers followed by 3 letters. Okay, so there's 10 numbers, so 10 possible numbers. Okay, 0 through 9, and 26 letters that we could use. So in part A, we just want to know how many different pins of that type are there. So we could just do our 3 numbers, and then our 3 letters. Okay, so numbers, letters, and then so the numbers each, because I have no restrictions, they're going to be 10 options for each. If you want to use 10, choose 1 for each of these. Okay, that's the same thing, so that's fine. Some people like to use the chooses. And then the debit for the letters, there's 26 options for each, or 26 choose 1 if you prefer. So then if you compute this, multiply all those together, you get 17,576,000. Okay, now part B, you have no repeated numbers and no repeated letters. Okay, so this and is important because you can't have any repeats in your PIN. You want to know how many are there of that type. Okay, well we could do the same thing if you wanted. Okay, so you still have the first 3 are numbers, second 3 are letters, but now your number of options are going to decrease because you can't reuse letters anymore, or numbers. So you're going to have 10 times 9 times 8 for the letter or the numbers, and then 26 times 25 times 24 for the letters. You could also write this as 10 permute 3 for the numbers, and then 26 permute 3 for the letters. So this is saying here, from your 10 numbers, select 3 different numbers where the order matters, because the pin 1, 2, 3 is going to be different than the pin 3, 2, 1. And then we also want to pick 3 letters to go along with that. So of your 26 letters, you want to pick 3 different ones where the order matters. Either way, you should get 11,232,000. Okay, let's try another one. How many different PIN numbers have either a 2 as the first number or as the last number? Okay, so this or is different than the and above. So this means that we could start with a 2 and not end with a 2, or we could end with a 2 and not start with a 2, or both. So there's different ways to do this. I think I'm going to use pi, okay, because it seems like a union. Okay, so these are my 2. So 2 is the first number, is going to be sort of A, and 2 is the last number, is going to be B. So then what we're looking for is the number in A or B. So it's going to be the number in A plus the number in B minus the number that are in both. So A is all the ones that have 2 as the first number. So you can do that with your 6 spots. I'm actually only going to do 4 spots because here the numbers don't matter. So it's going to be 26 times 26 times 26. So I'm just going to write that as 26 cubed for all of them. Okay, so letters don't really factor in here. Okay, but for the numbers, in A, we have 2 as the first number. So that means in our first spot, there's only one choice. It has to be a 2. But in the other spots, it may or may not be a 2, so there's 10 options. Okay, now in B, same idea. But now our 1 is in the third spot. That last number has to be a 2, and the others may or may not be 2s. So they have 10 options. But now I've definitely counted the pins that have 2s in the first spot and the last spot because I allowed this spot to be a 2. So that means I want to subtract the ones that have 2s in both. Okay, so that means they're both 2s, and then this middle number can be anything. Okay, if you do that, you should get 3,339,440 different pins. Now you could do this with cases. I don't have a lot of room here, but let's just see. So I'm going to erase this, I think, so we can talk about the cases. So if you want to split by cases, you just have to be careful. So you'd want the number that start in 2, okay, and not end in 2, plus the number that end in 2 and not start in 2. Okay, and then you'd want to also add the number that start, this is an and end in a 2. Okay, so you'd have to add up 3 things. You just want to be really careful when you're using cases that your cases don't overlap. Okay, so that's why we have these extra conditions here. So in order to make sure my cases don't overlap, I can't allow the start in 2 case to include it also ending in 2. Okay, so you just have to split it up more carefully. Okay, but you could do it that way. It would be a good idea to try and do it that way and make sure that you can still get the same answer because it's counting the same thing, so you should get the same number. Okay, last one of this type. So how many different pin numbers have the letters in alphabetical order? Okay, that's kind of tricky. So they don't have to be consecutive. Okay, so I'm going to write here, not necessarily consecutive. So what that means is that you could have like 3 letters, so A, O, and Z. Okay, that would be in alphabetical order. Okay, even though they're not consecutive letters. So let's try and do this. So the numbers, okay, they can be anything because there's no restrictions on the numbers. Okay, so those are easy. So just 10 choices for each. Now, if you try to do the letters spot by spot, you're going to run into trouble because once you get to the second spot, the number of choices depends on what you picked in the first spot. Okay, so if you picked, say, X, then it has to be X, Y, Z. But if you pick A, you have lots of choices for the second and third letters. Okay, so when that happens, you need to abandon that strategy. We're going to try and break it up a different way. So what we're going to do is select 3 letters, and then we're going to arrange them. Okay, so we just want to select 3 different letters, and because we're going to arrange them after, the order doesn't matter. Okay, so I want to do 26, choose 3 here. Now, once I have 3 letters, so let's say these 3 letters, how many ways can I put them in alphabetical order? Well, they have to go in that way. Okay, so arrange them, not all of the arrangements, but specifically in alphabetical order. So once I have 3 different letters, there's only one way to put them in the right order. Okay, so the order that we want here. Okay, so if you compute this, you should get 2,600,000 different ways. Okay, let's move on to something a bit different. A bag contains marbles. 7 are yellow, 6 are pink, and 2 are green. So that gives us 15 marbles in total. And we're going to grab a sample of 5 of them. So let's just write here, 15 marbles total. So how many different selections have exactly 4 pink marbles? Okay, so what we can do is split up our selection. So we're going to have 2 categories. So we're going to select 4 pink marbles, and then we're going to select 1 non-pink marble. Okay, so we know that there's 6 pink ones, and they're numbered. Okay, so they're all different. So from our 6 marbles, we're going to select, 6 pink marbles, we're going to select 4 pink ones. And then the non-pink category, how many are there? Oops, non-pink. So that's going to be 7 plus 2. So there's 9 non-pink ones. So from the 9 other ones, we're going to select 1. Okay, so if you do that, you're going to get 135 different selections. Now, how many have at least 4 pink ones? So remember, it's easier to count when you know exactly what's happening. Okay, so the number with at least 4 pink is going to be the number with exactly 4 pink plus the number with 5 pink. And we can't actually get more than 5 because we're only selecting 5 marbles. Okay, so it's only 4 or 5. Now, we want to add these numbers. Now, we already did the first one because that was actually part A. And the number with 5 pink, we're just going to pick 5 of the pink ones. And if you want, you can also write 0 of the other ones. Okay, but 9 choose 0 is a 1. Okay, so 6 choose 5 is enough. So we end up getting 141 total. Okay, how many with at most 4 pink marbles? So at most 4 pink means they could have 0 pink, 1 pink, 2, 3, or 4. Okay, so we get 5 different cases. Now we've done one of them, so there's 4 new ones to do. So you could do it like that, but it's going to be faster if we think about the complement. Okay, so the complement, so the opposite of at most 4 pink marbles is going to be, so this is less than or equal to 4 pink, so it's going to be more than 4 pink. Okay, so if you don't have at most 4 pink, it means that you have more than 4 that are pink, which actually is just that you have 5 pink because we're only selecting 5 pink marbles. So the number with at most 4 pink is going to be the number in the universe, so the universal set, minus the number in the complement, which is 5 pink. So the universe, we just grabbed 5 of the 15 marbles, so it's going to be 15 choose 5. And we already said that the number with 5 pink was 6 choose 5. So if you do that, you should get 2,997. Now, if you do it with the cases, okay, you should get the same answer. So if you wanted to do that for practice, that would be a good thing to do. Okay, let's try another one. Last one. 5 friends go to a salad bar and they're each going to order a salad. Okay, every salad has the greens, and then you get to choose 4 of 8 toppings. and you never choose the same topping twice. So first of all, how many different salads are possible? Okay, so there's 8 toppings that you can choose, and you want to choose 4. And obviously the order doesn't matter because they're just getting thrown onto the top of the mixed greens. Okay, so there's going to be 8 choose 4 or 70 different salads that you could make. So, in how many ways can the 5 friends order their salads? So no restrictions. So they may order the exact same thing, they may order different things. So we could just do the 5 friends one at a time. So they each have to place their order in order for the order to be complete. Okay, so this is friend 1, 2, 3, 4, and 5. So they each have to pick one of the 70 different available salads. Okay, so that's going to mean that they have 70 choose 1 options, okay, for each. So that's just 70. Okay, so it's actually 70 to the power 5, which is a really big number. Okay, 1, 6, 8, 0, 7, 0, 0, 0, 0, 0. Okay, so this is how many different orders they could make. Okay, what if the 5 friends wanted to order so that no 2 of them ordered the same salad? Okay, so they might have some ingredients in common, but they're not the exact same salad. So we could do the same idea, okay, where you have each of the friends does their order. So friend 1, 2, 3, and 4. And you just reduce by 1. Okay, so friend 1 has 70 options. The second one can't order whatever friend 1 ordered, so they only have 69 options. Okay, and you just keep going down. So 67, I'm going to go down to 66. This is the same as 70 permute 5. So you're choosing 5 different salads from the 70 possible salads, but the order matters because they're going to different people. Okay, so you want to know who ordered which one. Either way, you're going to get another big number. So 1, 4, 5, 2, 3, 6, 1, 680. Okay, different orders if they don't order the same thing. Okay, lastly, what if they want to order so that at least 2 order the same salad, exact same salad? So not just some ingredients the same, but the same salad. So if you think about at least 2 of them, okay, remember it's easier to count when you know exactly what's happening. So you might think, okay, what are the cases here? So we could have 2 the same, and then the other 3 different. Or we could have 3 the same, the other 2 different. Or we could have all 4 the same, or 4 the same and 1 different. Or we could have all 5 the same. Or you could actually have 2 the same, 2 the same, 1 different. Okay, and you can keep going like this. Okay, there's too many cases. Okay, while you might be able to count each one, there's just too many of them for that to be feasible. Okay, so it seems like a lot. So let's think about the complement. So what's the opposite of at least 2 friends order the same salad? So if you don't have at least 2 friends ordering the same salad, it means that every friend ordered a different salad. Okay, that's exactly what we just counted. Okay, so the number with at least 2 the same is going to be the number in the universe minus the number with all different. So where everyone ordered a different one. So this is actually part B is the universe, where everyone orders something with no restrictions. And where they were all different was part C. So I'm not going to write the numbers down, but if you subtract them, you should get 228,338,320 different orders. Okay, so if you're getting lots of cases, stop yourself and try to think about what the complement would look like.